As you know that the hydraulic turbine, that is the hydraulic energy to the mechanical energy. So hydraulic turbines are the machine which convert energy of water, that is hydraulic energy, to mechanical energy. So the mechanical energy developed by the turbine is used to run an electrical generator, and this electrical generator is coupled to the shaft of the turbine. So therefore the electrical generator will now develop electrical power, which is known as hydroelectric power. So therefore a turbine, it converts hydraulic energy to mechanical energy and to finally to electrical power. So in general, a water turbine consists of a wheel, which is also known as a rotor or a runner, having a number of specially designed vanes, buckets or blades, which is mounted on the periphery of that runner. So the water possessing a large amount of hydraulic energy, so when it strikes the runner, so it does work on the runner and causes it to rotate. So this mechanical energy which is developed is supplied to the generator, which is coupled to the runner, and which then generates electrical energy. So this is how the electrical energy is developed, um, which we'll discuss in detail in further slides. So what are the elements of an hydroelectric plant? So the essential requirement for an hydroelectric power generation is the availability of a continuous source of water with large amount of hydraulic energy. So such source of water can be available from a natural lake or a reservoir, which can be found at a very high elevation. Or you can construct an artificial reservoir by constructing a dam across a river. So now if you discuss about what is the general layout of a hydroelectric plant, it consists of an artificial storage reservoir which is formed by constructing a dam across a river. So now when the water is stored on the upstream side, the water surface in the storage reservoir is known as a head raise level, or simply known as a head raise, and water from the storage is carried through pipes. Large diameter pipes are also known as a penstock or canals house, and these penstocks are the pipes of very large diameter, usually made up of a steel or a reinforced concrete, which can carry water under pressure from storage reservoir to the turbine. So water after passing through the turbine will be discharged to the tail race. So tail race is nothing but a channel which carries water away from the powerhouse after it has passed through the turbines. So this tail race can be that means it can be sent to a natural stream channel, or you can have a specially excavated channel entering the natural stream at some point downstream from the powerhouse. So water surface in the tail race is known as a tail race level, or simply race. So this is what is the figure showing hydroelectric plant. So we have a constructed a dam across in a river. So there is a storage reservoir. So therefore the water level in the storage reservoir is known as a head raise. Okay, so now water from the storage reservoir is taken through a large diameter pipe, which is also known as a penstock. Okay, so penstock, and then we have a powerhouse which houses the impulse turbine or any other type of a turbine. After water hitting, the work is done. Okay, so then when after flowing through the turbine, it goes to the tail race. So tail race is nothing but any excavated channel, okay, which takes water out of the powerhouse to a nearby stream. So the water level in the tail race, that is in this channel, is known as a tail race level, or simply called the tail race. So whatever the difference between the head race and the tail race when no water is flowing is known as the gross head. Okay, is known as gross head. So this difference between the head race as well as the tail race is known as a gross head, and is also known as a static head, or also known as the total head. So when the water flows, there is always resistance to the flow. So there is always some loss. That means some energy is consumed, and hence loss of head takes place. So therefore, this loss of head is mainly due to the head loss due to friction. Head loss due to friction. So that's the reason why whatever the head that is available to the turbine is known as a net head. So after we deduct from the gross head the head loss due to friction, so then we get the net head. So henceforth net head is gross head minus head loss due to friction. So that's what we discussed here. So that's mainly the head loss is due to the friction in long pipelines. Head loss is due to the friction. That's the reason why. So there are other losses which is very minimal. So that's the reason why the net head is calculated from gross head minus head loss due to friction. So then the more important terms are known as the efficiency. So now in a turbine, we know that we give the power to the turbine, the power supplied to the turbine, which is also known as a water horsepower. So water is brought from reservoir to the through the penstock to the then issues from the nozzles. So that's why we have what is known as a water horsepower. That is nothing but, in case of Pelton wheel, it is a kinetic energy per second. So water will this energy is utilized in running the turbine. So therefore work is done on the turbine. So that is what is known as the power developed by the runner. So it is work done per second. This work done per second is utilized in running the electrical generator. So whatever the power that is available at the shaft is the output. So when you are supplying power to the turbine runner, so then work is done here. So this is output and this will be input. So there will be there is always output is less than the input. So therefore there is a loss that is taking place, that is known as a hydraulic loss. So ratio of power developed by the runner to the power supplied at the turbine entrance is known as hydraulic efficiency. So it is known as hydraulic. So output by input. So when you come here, work done is given to the again by then this will be utilized for developing a power at the turbine shaft. So the output is power available at the turbine shaft, whereas input is work done per second. So there is always mechanical losses that is taking place in form of a bearing friction. So therefore output divided by input. So that means power available at the shaft, that is shaft power, divided by work done per second, is known as mechanical efficiency. So when you take from first to last, that is the output is power available at the turbine shaft to the power supplied, that is water horsepower at the to the turbine entrance, that is water horsepower, is known as overall efficiency. So output by input. So this is how you remember by this block diagram. It is very easy. So now you can say that hydraulic efficiency is work done per second divided by kinetic energy per second. So here mechanical efficiency is nothing but power available at the turbine shaft divided by power developed by the runner, and similarly overall efficiency can be defined as power available at the turbine shaft to the kinetic energy per second or water horsepower. So now you know that overall efficiency is shaft power divided by water horsepower. You multiply and divide by work done per second. So therefore you can say that work done per second divided by water horsepower is nothing but hydraulic efficiency. Shaft power divided by work done per second is known as mechanical efficiency. Hence you can define overall efficiency as hydraulic efficiency into mechanical efficiency. So coming to the classifications of the turbines, so we have the classification of turbine based on various criteria. So therefore the first criteria is that according to the action of water flowing through the turbine runners, according to the action of water flowing through turbine runners, we have what is known as an impulse turbine and the reaction turbine. So here in an impulse turbine, all the available energy of water is converted into kinetic energy after it passes through the nozzle, which is provided at the end of the penstock. So water comes from the storage reservoir through a penstock. At the end of the penstock there will be a nozzle, so a jet of water is issued. So it comes with a very higher velocity, therefore the entire available energy is getting converted to kinetic energy. So now this water coming out of the nozzle is formed into a free jet, so which will impinge a series of buckets on the runner. So thus the runner will rotate or will revolve. So this runner is revolving freely in air. Hence the water throughout its action on the runner is atmospheric pressure, at atmospheric pressure. So but a casing is provided, so however, to see that there is no to prevent splashing and to guide the water from the buckets to the tail race. So this is known as the, because here all the available energy is getting converted to kinetic energy by passing it through the nozzle. So such type of a turbine is known as impulse turbine. So example is the Pelton. But in a reaction turbine, the second type is a reaction turbine. Here, at the entrance is only or at the entrance to the runner, only a part of the available energy is converted into a kinetic energy, and most of the part of the energy remains in the form of a pressure energy. So now, as the water flows through the runner, the change of pressure to kinetic energy takes place. So as such, the pressure at the inlet to the turbine is much higher than the pressure at the outlet. So and goes on varying throughout the passage of water from the through the turbine. So for a gradual change of pressure, the runner is completely encased in an airtight casing. So this is very much necessary in the case of a reaction turbine. So then the passages should be entirely full of water throughout the operation of the turbine. So now there is always a difference of pressure between the inlet and the outlet, which is called the reaction pressure and hence known as a reaction turbine. So the example for reaction turbine is called the Francis turbine or the Kaplan turbine. These are the two types of turbine which is classified under reaction turbine. So now this is what the case which was discussed. So therefore we have constructed a dam and there is a storage reservoir. From the storage reservoir, the water is brought from a penstock and then issued through a nozzle. A free jet is formed and which is striking the buckets. So now this runner is rotating freely in air, and most of the part is in atmospheric pressure, and therefore entire jet of water is converted into kinetic energy. Okay, so this is converted into kinetic energy, and after flowing through this runner, it goes to the tail race. So therefore here, but the casing is provided to see that there is no splashing of the water. Okay, and also to guide the water towards the tail race. So that's why this type of turbine is known as impulse turbine, which is the example is not but the Pelton wheel, which we'll be going to discuss in the later slides. So this is the case of a reaction turbine where again water is brought for the penstock, but there is nothing like the nozzle which is fitted at the end. So that means that is taken into the through the casing. So water is brought from the casing to the guide vanes and then it will be taken into the runner. So water will be as it flows in the casing. So the change of pressure from pressure energy to the kinetic energy takes place. However, the pressure at the outlet, okay, is getting converted, and then the pressure at the inlet will be quite different from the pressure at the outlet. So this difference of pressure is created between an inlet and outlet, which is known as a reaction pressure. That's why it is known as a reaction turbine. So therefore you need to guide the water to the tail race. We need what is known as a draft tube here. Okay, so it requires an airtight casing here, so that the conversion of energy takes place. So the Francis turbine and the Kaplan are the examples for this. And now that was the first classification. There is another criteria to classify according to the main direction of flow of water in the runner. We call it as a tangential flow turbine. So when the water is flowing, when it comes out of the nozzle, it tries to hit a pitch circle, which is called the path of rotation of the runner. When the water strikes to the tangent to the path of rotation of the runner, then it is called tangential flow turbine. So the example is the Pelton wheel. So when water flows along the tangent to the path of rotation of the runner, then it is called a tangential flow turbine. So here we have Pelton wheel as an example, that is an impulse turbine. So also in the second case we have what is known as a radial flow turbine. Here water enters radially either from outer circumference to the inner circumference or from inner circumference to the outer circumference. That will be in the radial direction, but remains in the plane which is normal to the axis of the rotation as it passes through the runner. Such type of turbines are known as a radial flow turbines. So in radial flow turbine we have two types, which is called inward radial flow turbine as well as outward radial flow turbine. In inward radial flow, the water enters inwards radially. That means water enters at the outer circumference and then moves towards the inner circumference, that is towards the center of the runner. Such an type of a turbine, radial flow turbine, is known as an inward radial flow turbine. Example is an old Francis turbine or a Thomson turbine. The second case is called the outward radial flow turbine. Here water enters at the center and then goes out outwards, radially outwards towards the outer circumference. So therefore, that is known as an outward radial flow turbine. For neon turbine is an example for outward radial flow turbine. So now this is what the case I was discussing for the tangential flow turbine. So these are the series of buckets that are mounted on the runner. So when you join the center of the buckets, we get a circle that is known as a pitch circle. So now the water is striking like this in this direction, like this, straight, and then it hits the tangent to this circle. So that's why it is known as a tangential flow turbine. Example is the Pelton wheel. So I was discussing about the radial flow turbine. Here the water is coming from the penstock and goes into the casing, and the change of pressure takes place. Now water is entering here. So that means this is the outer circumference, this will be the inner circumference. So water enters in this direction, so radially, but perpendicular to the your screen is the axis of the rotation. Therefore here water enters radially. So therefore it is called the radial flow turbine. From outer circumference to inner circumference, it enters inward radially. So therefore it is known as the inward radial flow turbine. Here, in the case of an outward radial flow, the water is entering at the inner circumference and going towards the outer circumference. So that is the path of the water is shown here. So therefore it is known as an outward radial flow turbine. There is also known as what is known as an axial flow turbine. So in the previous case, radial flow turbine, water was entering radially but moving out perpendicular to the axis of the rotation. But in the axial flow turbine, the flow of water through the runner is wholly and mainly along the direction parallel to the axis of the rotation. So when the water is moving out in the direction parallel to the axis of rotation, then it is known as an axial flow turbine. Example is the Kaplan turbine or a propeller turbine. Okay. In the mixed flow turbine, water enters at the outer periphery in the radial direction and then leaves at the center in the direction parallel to the axis of the rotation. So it's a combination of radial flow and axial flow turbine. Here water enters the outer circumference, moves radially, and then leaves at the center in the direction parallel to the axis of the rotation. So modern Francis turbine is an example for mixed flow turbine. So this is the sketch of an axial flow turbine. Water from the penstock is brought to the casing. From the guide vanes, water is thrown to the runner vanes. Here in this case, it consists of something like a hub where there are 4 to 6 vanes which are mounted onto this hub. Okay, so that is what is shown. So now water is entering in this direction, which is, this is the axis of rotation. So therefore it is parallel to the axis of the rotation. So therefore it is known as axial flow turbine. Okay, after water passing through this, will go to the draft tube, and from there it goes to the tail race. So this is the example of a Kaplan turbine, which is also known as an axial flow turbine. Then on the basis of the head and quantity of water required, so we have 3 types of turbine, which is called high head turbine, medium head turbine and low head turbine. So on the basis of the head, if the turbine is working under very high heads, say more than 250 meters, so then it is classified under a high head turbine. Since it is working under a very high head, so therefore it requires a very less quantity of water. So example is a Pelton wheel. If the turbine is working under a medium heads ranging from somewhere around 60 to 250 meters, then it is classified under medium head turbines. So this requires relatively large quantity as compared to the high head turbine. So therefore example is Francis turbine, which works under medium head. And there's also the turbines called as a low head, which is working under heads less than 60 meters, very low heads. So such a turbine is known as a low head turbine, and this definitely requires a very large quantity of water to develop the same power as the high head turbine. So therefore the example is the Kaplan turbine. So on the last classification is on the basis of a specific speed. You know that a specific speed is a speed of a geometrically similar turbine when working under a head of 1 meter will develop 1 kilowatt power. So that means you have to construct a model of a prototype. So turbine is constructed, then we work this model under a head of 1 meter. Okay, head of 1 meter. If then it develops 1 kilowatt power and the corresponding speed of this model is known as a specific speed, so that is what the definition of specific speed. According to that, a model of a prototype is constructed and we make that to work under 1 meter head to develop a 1 kilowatt power. So whatever the speed that is achieved by the model is known as a specific speed. So when the specific speed is between 8.5 to 30, so that is then it is a Pelton wheel with a single jet. If the specific speed is between 30 and 45, then we have Pelton wheel with multiple jets. Okay, so then if the specific speed is between somewhere around say 50 to say 300 or 340, then it is the medium head turbines, which is the Francis turbines. And if specific speed is greater than 300 and goes up to 860, so then it is a Kaplan turbine. So these are the various the various categories of classifications that these same turbines are classified under. So you saw that the Pelton wheel was an impulse turbine, and also it works because it is also a tangential flow turbine because the water is hitting tangent to the pitch circle like this. Then we had a case of a Francis turbine, which was the radial flow turbine, and also it works under medium head. And a Kaplan turbine is also a radial flow turbine, but it is an axial flow turbine where water is moving axially, that is parallel to the direction of path of the rotation, and it works under a low head. So it has different turbines has got different specific speed. When you prepare a model of that turbines and make it to work under a 1 meter head, then the corresponding speed is known as the specific speed. So depending upon the specific speed that is achieved in the laboratory or during the model testing, so we can have the various categories like Pelton wheel with single jet, Pelton with multiple jets, Francis turbine, and Kaplan turbine. So this is about the introduction to the turbines. Just a brief introduction to the turbines. So my next lecture will be on the one of the types of the turbines, which is known as the Pelton wheel. Then after covering Pelton wheel, I will go ahead with the Kaplan turbine, and then finally I may touch upon with inward reaction flow turbine, and last unit will be on the centrifugal pumps. Okay, so which will be covered in details. So hope you had a very nice session about the introduction to the turbine. I will come later with some of the videos on Pelton wheel.